Hi, welcome back to es346 Basic Thermodynamics. This is module 2.1, Forms of Energy. The corresponding sections in the textbook are Sungel and Bowles, section 2.1 and 2.2. Here's the course outline. We are in chapter 2, so we're here at the very first bullet item of Introduction and Background. There are 3 learning outcomes in this module. At the end of this module, you will be able to identify different forms of energy. You will be able to identify an energy transformation process, and you'll be able to calculate the energy stored in a pressurized fluid. So, let's start off with the definition. What is energy? A good definition of energy is the capacity to do work. That leads to, clearly, what is the definition of work? And work has a very straightforward definition as well. It is the force through a distance. So we can kind of think of this in a very simple way. If I had a surface here with, for example, a block. And if I was to go ahead and do some work on this, I could go ahead and exert a force on this block. Call that force F. The block would slide, and if there was friction, it would go some distance and perhaps stop there. And that would be a distance S. The work is the force through the distance, so therefore the work would be equal to that force times the distance, or F times S. Now, if we think of energy as a capacity to do work, that means something might, if it has energy, it has the ability to do that. So let's think of sliding this block again, but instead of me pushing it with a force, I'll have a rigid wall here, and then a spring attached to it that is coiled up. Now, if I was to release that spring would perhaps push the block forward, again, pushing it a distance S. How much work did it do? Well, the work would be equal to the force through the distance. Now, a spring, as you often know, sometimes has a stronger force when it is more compressed. So here what we would actually need to do is integrate the force through the distance. However, what we realize again is that the energy stored in here once we perform that integral E is stored in that spring. So we see energy is a storage of this capacity to do work. All right, let's look at several different forms that energy can take. I've listed several of them here, and I'll briefly go through all of them and give some examples. So, kinetic energy. Kinetic energy is the energy associated with something moving. So, for example, I could imagine a bullet coming out of a gun that would have a certain amount of kinetic energy. We can also talk about potential energy. That's the gravitational potential, so something that is at a higher elevation than its stopping point. So, for example, energy might be associated with a waterfall. It has potential energy at the top. Mechanical energy, which we're going to look at further in here, is one you may not have run across in physics before. But this is similar to that spring. It's energy that's in a compressed form that is able to push something forward. So, for example, we just saw mechanical energy stored in a spring. Thermal energy is the energy associated with something being hot. So, for example, a cup of coffee, if we just got it and it's hot, we would say that it has a lot of thermal energy. Electrical energy, electrical potential, would be something that's at a higher voltage. So, for example, a transmission line that may be at, say, 100 kilovolts has electrical energy associated with that. We also have chemical energy. That might be, for example, in a battery or maybe even in gasoline, as it's going to change its chemical form. Nuclear energy. Uranium-235 is the best example of nuclear energy. And magnetic energy is associated with magnets. Now, you may notice that I have listed 3 of these forms of energy in gray. The reason for that is we won't really be looking at these forms of energy further in this class. Now, although we may be looking at systems that have that energy in particular, they won't be transferring energy out of it or into that form. We'll be focusing primarily on these top 5, kinetic, potential, mechanical, thermal, and electrical. All right, let's talk about an energy transformation process. That's what we're really fundamentally interested in thermodynamics. So we will often start off with writing what our total energy is in our system. So for example, the total energy, I'll give it this symbol capital E. And as we just mentioned, energy can take various forms. And so here I'm going to start listing on the right-hand side the various types of forms that it has. So this capital U, you'll see, is associated with thermal energy, or what we will call internal energy. Ke is kinetic energy. He is potential energy. And I can continue to write the rest of those forms down. Now, as we'll see, I'll only need to include the terms that might be changing during a transformation process. So, for example, as we'll go through here, I'll just go ahead and stick with these three forms that energy may take: the internal, kinetic, and potential. So let's consider, for now, a ball. It will be a big rubber ball some distance above the ground. And I was to go ahead and release that ball. That ball initially has potential energy associated with gravity. The ball would begin to move down. As the ball moves down, it is going to decrease in potential energy and increase in velocity, increase in kinetic energy. So here it is doing an energy transformation. It's going from potential energy to kinetic energy. And that transformation process would continue until we're right at the bottom, about to hit the floor, where all that potential energy has now turned into kinetic energy. So there's now no potential energy at all. Now if this ball was to go ahead and bounce back up, so I'll draw that over here, it begins to move upward. I'm now going to go ahead and be turning some of that kinetic energy back into potential energy. And there I've got a transformation process going potential to kinetic to potential. And if the ball kept bouncing back and forth, you can imagine that keeps happening. Now, one interesting thing that comes up is to think about what happens at the instant this rubber ball is squished on the bottom throughout the bounce back up, so it's on the ground. As we just said, there's no potential energy at this point. It's gone to zero. But there's also no velocity. So that means that the kinetic energy has gone to zero. So a question may be, well, where is the energy stored? It's actually stored in all those squished up elastic bonds in the rubber. So this is a time when it actually has mechanical energy. So what we've done actually is gone potential to kinetic to mechanical to kinetic to potential energy. All right, let's do a simple example where we'll actually quantify the amount of energy. So here the question says, how much kinetic energy is there in a 10-gram bullet at 300 meters per second? Why don't you go ahead and pause the video for a second and think about how you would quantify this. Okay, well, what we're asking for here is the amount of kinetic energy. So we know from physics that kinetic energy is equal to 1/2 mv squared, where it's 1/2 times the mass times the velocity squared. Well, we're actually given the mass and given the velocity, so we can go ahead and just plug those numbers right in. 1/2, 0.01 kilograms, which is 10 grams, and a velocity of 300 meters per second squared. If I go ahead and multiply that out, I realize that is about 450. The units are kilograms, meters squared per second squared. And that unit is the same as a joule. So this would be 450 joules. Well, one common question after doing this is, well, how much is 450 joules? Well, to give you an idea, if I had a large cup of coffee and I was to go ahead and add 450 joules to it, it would increase in temperature about 0.1 degrees Celsius. So not that much. A whole lot of kinetic energy really is not that much thermal energy. Okay. I want to look a little bit more at this mechanical energy, the energy associated with something being compressed. And in this class, we'll be looking a lot at fluids. So let's imagine here that I have a cylinder full of a fluid inside, and then I have a piston attached to this. It's very tightly fitting. So if I was to add energy to this system, what I could do is exert a force on this piston, causing the piston to move this way and the volume to decrease. And we're assuming all the fluid remains inside this cylinder. If I want to quantify that amount of energy or the amount of work that I'm doing, I know that I can always integrate the force through the distance that I travel. So here the distance I'm traveling is ds, and I'm exerting a force F. Now, if I want to know what that force is, I can associate it with the pressure inside here. So remember, pressure is force per area, so therefore force is pressure times area. So for this force here in the integral, I can go ahead and put the pressure times the area times ds. The area is this cross-sectional area of the piston. ds is that. So I realize what P times A times ds is actually the integral of the pressure times the change in volume dV. So to go ahead and perform this integral, I would need to know how the pressure changes. Now, as this gets more pressurized, the pressure, we know the pressure should go up, and we would need some relation. We'll look later at the class at different types of relations for the pressure of volume. But for now, what we'll do is we'll just assume that the temperature remains constant. And therefore, what I know is I can replace the pressure with a constant over the volume, where the constant is truly that. It doesn't change. So now I'm going to quantify what the work is. It's going to be the integral of a constant over v dv. I can take the constant out of the integral. This becomes c, and the natural log of v2 over v1. And that constant, if it's a constant temperature, from the ideal gas law, I know that PV is equal to mRT, which is equal to that constant. So that constant is, for example, P1 V1. So I can now say the amount of work done, I take my initial conditions, P1 V1, multiply it by the natural log of V2 over V1. Okay, let's do an example for this mechanical stored energy of a fluid. In this example, asks for how much mechanical energy is there in the 3000 psi gauge scuba diving stage. Go ahead and pause the video for a minute and maybe do this problem on your own, and then we'll work through it together. Okay, what we just saw from the previous, the amount of energy that's associated here would be the mechanical work, which we know is P1 V1 natural log of V2 over V1. So what I need to know in this problem are what the initial and final volumes are and what the initial pressure is. I'm explicitly given the initial pressure, but I'm not told anything about the volume. So I would need to know what that is. Well, I know, I used to be a scuba diver, that the volume of a scuba diving tank is about half a cubic foot. So that right there is the initial volume. But now we need to know what the final volume is in order to calculate the amount of work that was done. Now, again, we will assume a constant temperature, which allows me to use the combined gas law that says P1 V1 equals P2 V2. Or therefore, to find out what V2 is equal to V1 P1 over P2. And if I put those numbers in, 0.5 cubic feet. The initial pressure is 3000 psi, which would be 3015 psia over 15 psia, which would be atmospheric pressure. And that number right there is equal to about 100 cubic feet. Now I should pause here for a moment and notice I changed the gauge pressure to absolute pressure. You may wonder why. The reason I did that is this relation I'm doing here is from the ideal gas law. And those need to be absolute pressures. It also becomes clear if I was using gauge and I put 0 in here, I would have had an undefined number. So my final volume is 100 cubic feet. So now let's go ahead and plug it in to find out the amount of energy stored in there. It is the initial pressure, which was 3015 psia. The initial volume, 0.5 cubic feet. Natural log of the second volume, which is 100, the initial volume of 0.5, and that right there is equal to about 8,000, and my units would be psia cubic feet. So that is a unit of energy, a unit of work. It's not one you run into very often. We could go ahead and do a unit conversion into a more common English unit, and this is equal to approximately 1,500 BTUs, or British thermal units. Now, is that a lot of energy? It's a good question. Well, this again I know from when I taught scuba diving. If I was to take an average vehicle that weighs about 4,000 pounds and put that much energy into this car by maybe putting the scuba tank underneath it and having it explode, how high would that car go? It would go about 288 feet.